Hi, welcome everyone. This is we are continuing on our course on principal stresses and strain. Just a quick recap on what we have covered so far. We have looked at the definitions. We have understood that the principal planes are planes where shear stress is zero, and they only have normal stresses, and those stresses are called principal stresses. We went on to understand that there were analytical and graphical methods that we could use to identify them. And we have covered the first analytical method where a member is subjected to a direct stress in one plane. We have looked at these and we have got the equations for sigma n, sigma cos square theta, and sigma t, sigma by 2 sine 2 theta. And I will look at, in this video, we'll look at the second method where a member is subjected to like direct stresses in mutually perpendicular directions. Now, let's move on to the whiteboard where I will take you through the derivations. Now in this we will consider a member ABCD of unit thickness, and let us assume that there are two loads acting on this. One is P1, which is acting axially, and another one is P2, which is acting perpendicular to this. I mean, we need two mutually perpendicular loads to create two mutually perpendicular stresses. So let us assume that the stress created by P1 is sigma 1. And the stress created by P2 is sigma 2. All right. Now we are interested in an oblique plane and what kind of stresses are applicable in this oblique plane. All right. Let us assume a plane FC which is at an angle theta with BC. Now our approach has always been to consider a plane which is perpendicular to the line of action of the force, work out the stress on that plane, and then using resolution of forces transfer that stress onto FC and find out what impact it has, and then find out sigma n, which is normal stress to plane FC, and sigma t, which is the tangential stress on plane FC. That is how our approach has been. So let us take that approach. Let us look at that approach. I mean, first of all, the impact of P1 on plane FC and the impact of P2 on plane FC is what we look at. Now let me just draw this separately here. If I have this as plane FC and I have this as P1, yeah, with the perpendicular, P1 will have an angle of theta. Yep. And then we can resolve this into its components. This will become P1 cos theta, and this will become P1 sin theta, which will be in the direction of plane FC. And similarly, P2 can be resolved into its components along FC. This angle will be theta, so you can have this will be P2 cos theta, this will be P2 sin theta. All right, now we can write P1 and P2 in terms of sigma 1 and sigma 2. Let us try and do that mathematically. P1, you can say it is sigma 1 stress times area of face BC, which is equal to sigma 1 BC times 1, unity being the thickness. Now similarly, tensile force on face FB, if you look at P2, it will become sigma 2 times area of face FB, which is equal to sigma 2 times FB times 1. Right? Now, the tensile forces P1 and P2 are also acting on the oblique plane. We have just resolved them into its components. And now let us look at the forces normal to plane FC. Pn will be the sum of the impact of these two forces, that P1 and P2. So in the normal direction, it will be the sum of P1 cos theta and P2 sin theta, which are normal to the plane FC. So it will be P1 cos theta plus P2 sin theta. Now if we substitute P1 and P2 in this equation, we will get sigma 1 BC cos theta plus sigma 2 FB sin theta. This is Pn. Right? Now similarly, Pt is the tangential force acting on section FC. It will be the sum of the components along the section FP. So it will be P1 sin theta plus minus P2 cos theta. We're taking minus because the directions are opposite. So if you have taken one direction to be positive, the opposite direction will be negative. So this brings us to P1 sin theta minus P2 cos theta. Now substituting the value of P1 and P2, we get sigma 1 BC sin theta minus sigma 2 FB cos theta. Now our fundamental objective is to find out the normal stress and the tangential stress across section FC. So sigma n is our normal stress across section FC. This will be equal to the total force on section FC by area of section FC. So the total force on section FC is the force that is acting normal, which is Pn, by the area of section FC, which is FC times 1. Unity being the thickness. Now Pn, we can substitute the value of Pn, sigma 1 BC cos theta plus sigma 2 FB sin theta by FC. Now we can resolve this further. Sigma 1 BC by FC cos theta plus sigma 2 FB by FC sin theta. I've just split it and written BC by FC and FB by FC in a fashion where I can now convert this into our sine and cos language. Now if you look at the triangle FCB, your BC by FC will be cos theta and your BF by FC will be sin theta. So substituting that here, cos theta plus sigma 2 sin theta times sin theta. You get sigma 1 cos square theta plus sigma 2 sin square theta. Now we know from trigonometric relations sine square theta and cos square theta can be replaced with sigma 1. Cos square theta will become 1 plus cos 2 theta by 2. and sine square theta will become 1 minus cos 2 theta by 2. So simplifying this further, you get sigma 1 plus sigma 1 cos 2 theta by 2 plus sigma 2 minus sigma 2 cos 2 theta by 2. Now simplifying further, I get sigma 1 plus sigma 2 plus sigma 1 cos 2 theta minus sigma 2 cos 2 theta. Now, if I can write sigma 1 plus sigma 2 by 2 plus I can take cos 2 theta, sigma 1 minus sigma 2 by 2 and cos 2 theta. Right, so I've simplified. This becomes my equation for sigma n. This is my equation 1. And now similarly, I can find out tangential stress, which is nothing but the tangential force acting along section FC by section area of section FC. Now the total force acting along section FC will be equal to the sum of the individual forces or the components of the forces PT by FC times 1. Now PT is sigma 1 BC sine theta minus sigma 2 FB cos theta by FC. Now what we did earlier will follow the same pattern. Sigma 1 BC by FC sine theta minus sigma 2 FB by FC cos theta. Now if we go back to our triangle FCB, we are looking at BC by FC, which will be cos theta, and then FB by FC, which will be sine theta. So this time we get sigma 1 cos theta sine theta minus sigma 2 sine theta cos theta. Okay, we can take sine theta cos theta common, so you get sigma 1 minus sigma 2 sine theta cos theta. Right, now multiplying and dividing by 2, you get 2 sine theta cos theta. 2 sine theta cos theta is cos 2 theta. Sorry, sine 2 theta. My mistake. So this becomes your sigma t. Now, if you look at sigma n and sigma t along plane FC, like for example, this is your plane FC, you will have sigma n. So your sigma n will be like this. This will be sigma n. Now if you have sigma t, you can resolve it. This is your resultant. So your resultant sigma r will be equal to square root of sigma n square plus sigma t square from our Pythagoras theorem, this being 90 degrees. So this angle is considered as phi, which is also called obliquity. Yeah, so that is nothing but the angle made by the resultant stress with the normal of the oblique plane is known as obliquity. It is denoted phi. Phi, mathematically, you can calculate tan phi is equal to sigma t by sigma n from trigonometric ratios. Now, let us look at the maximum shear stress. sigma T max.